Hello, this is Ms. Nichols, and this is the second lecture on magnetic induction, specifically focusing on magnetic flux, which is like a new tool to use to figure out the induced current and voltage in a wire that is moving in a magnetic field. And flux is a more powerful and versatile tool than the one that we learned about last time. Okay, so magnetic flux is a new variable. We use the Greek symbol phi to represent flux, and it is defined as sort of the amount of magnetic field that is passing through like a surface area, which is usually the shape of the circuit. So whatever dimensions the circuit has, that's usually going to be your circuit area. Flux actually can be a variable that we use in different units. You could talk about fluid flux, which would be the amount of fluid passing through a pipe. Magnetic flux is similar, except it's the amount of the magnetic field that's going through the pipe. Another way to think about this in terms of the spaghetti analogy is basically the number of spaghetti pieces that are poking through the hole created by the circuit. Phi has a linear relationship with B, so obviously the stronger the magnetic field, the more of those little spaghetti pieces are going to be poking through the circuit. And it also has a linear relationship with A, which is the area or size of the circuit, which makes the equation for magnetic flux, phi sub B, equal to B times A. So that's the external magnetic field, and A is the area, typically, of the circuit. Flux is a vector as well, so you would have a direction, and that direction is going to be the same as the direction of the magnetic field, because area does not have a vector, is not a vector. And the units for flux are going to be the Tesla, which is the units of B, meter per second squared, or sorry, Tesla meter squared, which is the same as a Weber, sometimes abbreviated WB. Let's run through a really quick sample problem for flux. Let's assume we have a square loop of wire that is 2 meters long on each side, and it is fully inside this magnetic field that has a strength of 5 Tesla. Calculate the magnetic flux through this loop. Well, phi is going to be equal to 5 Tesla multiplied by the surface area of the loop, which is 2 meters by 2 meters, and that gives us a flux of 20 Webers into the page, because that's the direction of the magnetic field. So the way we can use flux to talk about inducing voltage and inducing current in a circuit or in a loop has to do with whether or not that flux is changing. Since the flux is measuring how many of these spaghettis are poking out through the loop, anytime the total amount of flux, or the total amount of spaghetti in the loop, is changing, we know that those field lines or the spaghetti has to have been chopped, because there's no way you can get field lines into a loop or out of a loop without passing across the wire. So the key thing is whether or not the flux is changing. That's what's going to determine how much voltage and what the direction of the current is induced in the loop. On the flip side of the coin, if the flux is not changing, we have no current. And that's the example we actually did in class the other day, right? So that wire's moving, spaghetti is technically being chopped, but the flux isn't changing because the amount of spaghetti that's passing through that loop is the same at position 1 as it was at position 2. And that tells me that we actually have no current going through that wire. And we solved that problem with the sort of the longer, clunkier way, realizing that one of those wires was chopping spaghetti, the other was like negatively chopping spaghetti, or you could imagine them as batteries that were both trying to push the current in opposite direction. But no matter which way which perspective we take on this, whether we talk about it from a flux perspective or from an individual little wire perspective, no current is generated unless the flux is changing. Specifically, the rate at which the flux changes, so how quickly the amount of spaghetti through the loop is changing, is going to determine the amount of voltage that is induced, or the amount of current that is eventually going to be induced in the loop as well. So there's an equation on your equation sheet. E stands for the induced voltage, just like it did in the last lecture that we talked about. And E is equal to the rate of change of flux. In other words, the delta flux divided by the amount of time it takes. So the quicker the flux is changing, the more voltage is going to be induced, and eventually the more current is going to be flowing as well. And the slower the flux is changing, the less current and less voltage. That E, remember, is voltage. That's the induced voltage in the circuit. And of course, if flux is not changing, that all ends up being 0 as well. The voltage that we just found, that E value in that equation, can be combined with the resistance of the circuit. So I didn't put a resistor in there, but the wire itself has some resistance. And those two variables together using Ohm's law can determine the induced current through the loop. So just a reminder that E is a voltage value. You would be plugging that E in right there in Ohm's law, along with the resistance from the circuit to calculate how much current is actually going through it. One point that's going to become really important here in a few minutes is in this process, in the process of creating current in this loop, you've now turned this loop itself into a little magnet. So this is like the little test magnet. It's moving around. We made a magnet by moving this loop through this magnetic field. And this little new magnet is going to make its own magnetic field because we now have current moving in that wire. And that magnetic field is going to be pretty important, as you will see in a few slides. So let's look at some common scenarios in which we would have the flux through a circuit changing. There are sometimes scenarios in which the area of the loop itself is changing. Like they've got some weird flexible wire. Sometimes the wire is made out of like a slinky or something weird. But in general, if the wire itself is shrinking or expanding, then obviously the flux is changing as well. I showed that wire somehow stretching out and getting made bigger, and clearly that's going to be increasing the amount of flux through that loop because there's going to be more surface area for that flux to go through. Another scenario is that we could have a wire loop that is either entering or leaving the field, and that would change the amount of flux through the loop as well. So in this animation, I show the wire loop leaving the field. Obviously, in that case, we are going to be decreasing the amount of flux through the loop because we don't have any area overlapping with the field. And another scenario that sometimes occurs is that we have the wire loop in the field, but it's rotating. And that's essentially going to be changing the surface area of that loop that's perpendicular to the magnetic field, that should say, not to the loop. And the magnetic field's only going to be able to go through the loop if it's perpendicular, right? If the loop is parallel to the magnetic field, it's just going to skim through the side. So if the wire loop in the field is rotating, that would also be a scenario where we would have changing flux. So these are all cases in which we will be generating current, right? Delta flux is not 0. Thus, we will have induced current in these cases. Of course, we could also have scenarios in which the magnetic field itself is changing. If that magnetic field is made with an electromagnet, we can just adjust it occasionally. Or if we have like a permanent magnet, for example, or really an electromagnet too, if we are moving our loop closer or further away from that source magnet, then the field would be getting weaker or stronger. And that also is an example of flux that would be changing and causing current. As we move into the next portion of this, we're going to be talking about how to determine the direction of the current that is generated in these changing flux situations. It really boils down to something known as Lenz's law. And Lenz's law tells us kind of where a lot of these equations come from when you go back all the way to conservation principles. And Lenz's law was originally derived as a consideration of conservation of energy. And the idea is, of course, as always, energy is conserved, but it's going to be conserved when you have current being induced in a loop of wire as well. When you're doing this, creating this electrical current, the electrical energy, the current that you're making, or the voltage, has to come from somewhere. And it actually comes from the kinetic energy of the moving loop. So it's the force, it's the movement of that loop that is going to be converted into electrical energy. There's a couple implications of this. If we are inducing current from motion, the motion has to actually slow down, right? We've got to, excuse me, suck some of that kinetic energy out of the movement of the coil or loop, or we at least have to be pushing on that coil loop to make it keep moving at the same speed. And consequently, there will be a force that is resisting the movement of the conductor into that field. So you can actually feel this, and I'll do some examples in class as well. I'll show you guys some demonstrations of how when you do induce current, when you create current in a wire, you feel it. You have to actually really be pushing that wire in order for that to happen. So this is the force that is doing the work, right? Work is a force times distance, and that is the work that is transforming the kinetic energy of the coil or of the magnet into electric energy that we can use. There's a second implication that we'll be working with a little bit more than the first, and that is that the direction of the current that you create will create its own magnetic field that I mentioned a couple slides ago, that also resists the change in flux through the loop. So there's a lot to unpack in that sentence, and I'm going to come back to it in a minute a couple times. But realizing that we talked about flux changing, okay? Sometimes the flux is increasing, sometimes it's decreasing, and in different directions. And Lenz's law says we're going to make a new magnetic field. My current that I create is going to make a new magnetic field, and that's going to try to counteract the change in the flux through the loop. We're trying to stay at this equilibrium level that we started with. We're trying to avoid changing the flux, or at least that's what the induced field will do. A point that will be useful later on to remember is that if the flux through the loop is decreasing, then what this means is the induced field is going to be in that same direction so that we can bring it back up to its original level. Whereas if the flux through the loop is increasing, well, then my induced field is going to be in the opposite direction, so we can kind of cancel out that increase and bring it back down to its nominal level. So let's do some sample problems. This is actually the same problem we set up earlier with that loop moving sort of out of the field. So if we calculated that the flux through the loop at position 1 was 20 Webers in, when we've moved down to position 2, now we have a flux of only 5 Webers in, right? So we would describe that as a decreasing in flux, right? In order to counteract it, Lenz's law says that there's going to be some current that starts flowing in the loop, and the current that's flowing in that loop is going to try to resist the fact that my magnetic field went down. It's going to add some magnetic field back in to resist the change of flux in the loop, right? So we had less in as that thing slid out, and therefore the current is going to create a magnetic field in that space, in the space of the center of the circuit, that is directed in to basically try to bring it back up to where it was when the whole loop was inside the circuit, or inside the magnetic field. We'll go through a few more examples of that. So if this felt awkward, we'll do it a few more times. So here's another example of a way we could change the flux through a surface. This is known as a rail or a rail gun. It's essentially like a it's three sides of a circuit, and then it's the fourth side that's actually movable. It's like sitting on top, and it can slide in and out. And so we have this rail in a magnetic field that is into the page, and so that rail, you'll see, is actually going to be moving to the right, right? It has a velocity that moves to the right. So when it was at position 1, which is kind of the dash line, the before position, let's assume we had 20 Webers of flux going through it then. Now we're at position 2, and we've got more flux still going in because we've opened up that loop. We've made a bigger surface area, and so now we have increased the amount of flux in the center of that circuit in the direction in. So since we increased the flux in, we have to somehow counteract that according to Lenz's law. Lenz's law says that in that center of the circuit, we're going to create some opposite direction field lines, anti-parallel to the in magnetic field, in order to resist that change in flux that happened through the loop. So in the center of that circuit, we're going to create, just out of, on conservation of energy, we're going to create some outward directed magnetic fields to counteract the increase in that happened when we opened that circuit up a little bit more. This table, I'm not going to go through the whole table, but it's kind of a summary of what I've just been talking about there a little bit, that describes how you can use the change in flux in the circuit to determine what the direction of the induced magnetic field. So this is the magnetic field created by the current in the wire, and you want to figure out what direction that induced field is, and you'll see why in just a minute. So these are the couple problems that we did. If that field is decreasing in the in direction, well, we've got to have an induced magnetic field that adds some more to bring it back up. So that's going to be in. If the change in flux is increasing in the in direction, well, the induced magnetic field is going to be out to kind of bring it back down to normal. If you're decreasing in the out direction, well, then we do have to add some more out to make it back, to counteract that or resist that change in flux. So you can go through the whole table here, maybe try it on your own and see if you get the same answers that I got. Okay, so now that we figured out the direction of the induced field, you can use that with the first right-hand rule to determine the direction of the current. So this is kind of the reverse scenario with what we originally did with the first right-hand rule. When we first came up with the right-hand rule, we had wires and we wanted to know what the magnetic field around those wires looked like. So we would point our thumb in the direction of the current and our fingers wrap around that wire so we can see how the magnetic field curls around the wire. Well, this is the reverse situation. Okay, we now have this loop, and we know it's got some current in it, but we don't know what direction that current's going. What we do know is, what does the magnetic field that that current made looks like? So we're going to start with the magnetic field. We start with our fingers, and we're going to wrap those fingers around the wire to figure out which way your thumb is pointing, to figure out which way the current is going through the wire. So in that first scenario where we induced a magnetic field that was going in, okay, so the decreasing in flux meant that the induced field was also in, to kind of cancel out that change, right? According to Lenz's law. So what you're going to do here, imagine this is drawn on your paper. You take your fingers and you're going to poke them into the center of the loop, because that's what the induced field is doing. And then you kind of imagine that you grab the loop, grab part of the loop. In this case, I'd be grabbing the bottom wire of the loop probably, because that's the way my hand sort of works. If I imagine my fingers pointing in the center of that circuit and grabbing the wire I would end up grabbing is the bottom wire. And my thumb is going to then show the direction of the current in that wire. So my thumb would be pointing to the left. You could repeat the same process by grabbing any wire. Like I could rotate my hand, still have to keep my fingers in, grab that side wire, grab the top wire, grab that awkward wire on the side. What you should end up with is consistent path for the current to flow. In this case, this is a counterclock. Oh no, it's actually clockwise. Gosh, love these typos here. So this is actually a clockwise circuit in this case, as all of those arrows are pointing in the same direction. But you really only need one to figure out what's going to happen with the rest of them. The other example that we did showed that we had an increasing influx, and therefore the induced field had to be out to cancel that out. So what I would do is bring my fingers coming out of the page, or out of the page if it's flat on front of you. And then I'm going to grab whatever wire is convenient. Again, it's probably going to be the bottom wire for me. And my thumb is going to show the direction of the current through that wire. So this current is basically going to be going that way. If you did the other wires, you would discover, again, that current continues going in the same direction around the loop. This one actually is the counterclockwise loop as it goes around that circuit. Let's do one more example that kind of brings it together. with a couple other things that we learned. So let's say we have a wire loop that is perpendicular to the page. So it's hard to draw this, but you know, the wire loop is coming in and out of the page here to a bar magnet that is shown. And we're going to take that bar magnet and move it towards the loop. And the question is, what is the direction of the induced current in the loop? Well, the magnetic field, or the magnetic field in the region of the loop is acting to the left, right? Because we know that magnetic field lines leave north poles and come back in south, or they point in the direction that a north pole would point, so a north pole pointing towards that south. So that means that the magnetic field is actually going to the left through the loop. And that field is going to be increasing as the magnet gets closer, because it's getting stronger the closer we get to the magnet. Therefore, to cancel out an increasing field to the left, the induced field in that loop must be to the right. So those right arrows show the direction of the magnetic field created by the current that we are creating in that loop. I cut off the front half of this loop just so you could see a little bit better what was going on, because the last step is to do our right-hand rule. And what I would do is I would just pick one part of that loop, either the top or the bottom, and what you want to do is point your fingers to the right in the center, in between those two wires, okay? And then I'm going to grab a wire. In this case, I'm grabbing the top wire because that's the way my fingers are curling. Grab that top wire, and I'm going to find that for the top wire, my thumb is pointing out of the page. Therefore, current would be coming out of that top wire. If you wanted to, you could convince yourself, of course it has to be going in a circle, so it has to be going back in the bottom wire, but you could convince yourself of this as well if you found a way to rotate your hand so you could grab the bottom wire, right? So my fingers are still going to the right, and now I'm going to grab that bottom wire, and my thumb is going to be pointing into the page, so that current is cycling this direction, basically based on the fact that we moved that magnet. So hopefully this example and the ones that we ran through earlier make good sense to you guys, and we'll do a lot more practice in class. Thanks for watching.